Section 5.2, Random Variables. Previously, we made the distinction between a measured variable was continuous or discrete. Just to make sure we remember, we will distinguish between the following variables. For a quick recap, a continuous number is something that has to do with a measurement and is not a counting number like 1, 2, 3, 4, 5. That doesn't mean that decimals can't be discrete. 1, 1.5, 2, 2.5, that's considered discrete if there's no other decimal places after the 0.5. But something continuous is potentially will always have the measurement where decimals could go on and on and on and on. So let's see if we can make that distinction here with the few examples we have. Example 1, determine whether the following are continuous or discrete. A, the cost of a randomly selected tomato. Well, think about the price of a tomato, even if there's a certain per pound weight, maybe $1.99 per pound. Because of the way our money is, we stop at the nearest cent. So it could be $1.98 or $2.57. But we're not going to get anything like 2.57328 because that's not how our money system works. So because we stop at the nearest cent, this would be considered discrete. Now, if we were talking about the weight of the tomato, that would be continuous because we could always get to the nearest pound, the nearest tenth of a pound, hundredth, thousandth, and so on. We could always make it more and more precise. But because of the way we record money and we stop at the nearest cent, that's still considered discrete. B, the number of cars on the road with hybrid technology. Well, if we started counting the number of cars, 1, 2, 3, 4, 5, 100, 1,000, it's always going to be a whole number, and because there's no decimals involved that go on for several places, that's also going to be discrete. C, the lung capacity of non-smoking patients. Well, this would be a measurement, and we could get down again to the nearest tenth or 100th, or we could keep going with that decimal to be more and more precise. So this would be continuous. D, the total time a customer spends waiting in a grocery store checkout line. Well, maybe we might think of it in terms of minutes, but we could also get down to seconds, and we could also get down to the nearest tenth of a second, the nearest 100th of a second, and on and on and on, similar to the measurement we had with the lung capacity. So this again would be continuous. And E, the number of goals scored in a soccer game. Something countable, 1, 2, 3, 4, 5. We can't have 1.5 goals, and we're not going to go past a whole number, so this would be discrete. Okay, well, in this chapter, in chapter 5, we're going to concentrate on discrete variables, and we'll also look at some specific discrete distributions. But just in chapter 2, we're going to concentrate on some basic principles that apply to all discrete variables. So we're going to combine our knowledge of frequency distributions that we did back in chapter 2 and probability back in chapter 4 to construct probability distributions. But before we get started, let's define a few terms. Previously, we considered the experiment of rolling a fair die. We know that the die could come up as a 1, 2, 3, 4, 5, or 6 with varying probabilities. Now, if it's a fair die, we decided that each number was equally likely to come up, so the probabilities were 1/6. But we sometimes, if a die is loaded, that might not be the case, but in any case, we could assign a probability to each different outcome. What we're talking about here with random variables is we're going to let x represent one of the numbers that could appear. So x can take on the value 1 through 6. The variable x is called a random variable because it can only take on a single numerical value, representing the outcome of the procedure, as I just mentioned, but it's totally determined by chance. So we have, every time we roll that die, we have no idea which number will show up, and it doesn't even matter what came up on the previous die, it's always going to be by chance. So that's our random variable. Now in our die rolling experiment, we concluded that the probability of each number appearing was 1/6, as I just mentioned. Once we organize each respective probability with its random variable value, we have created a probability distribution. This can be in the form of a table, a graph, or a formula. Probably a lot of what we see will be in table form, but they also can be represented by a graph where you graph the bars, almost like a histogram, or as a formula. Well, just as with basic probability, the same rules and properties apply. So a few things I want to remind you about. The sum of all the probabilities of an experiment have to sum to 1. Same is true with the probability distribution. No matter how many values the random variable could take on, ultimately they all have to sum to 1. Then we also learn that each individual probability of x must be between 0 and 1. So probabilities must be between 0 and 1. So I cannot have a negative probability, and I cannot have a probability larger than 1. So all probabilities must be between 0 and 1. Example 1. Determine if the following are valid probability distributions. If not, determine the property that is not met. So the two things we're checking, and it doesn't matter which order you do it in, do the probabilities sum to 1, and are each of the individual probabilities between 0 and 1. Well, usually checking if they're between 0 and 1 is the first thing I check because it's easy and it's pretty obvious. So looking at this first distribution here, I have 4 possible values that the random variable x could take on, and each probability looks okay. It's positive, nothing's bigger than 1, so that property has been met. Well, let's make sure that they all sum to 1. So we're going to add up 0.037, 0.2, 0.444, and 0.296. Well, I get a sum of my probabilities equal to 0.977. Although that's close to 1, it's not close enough. It's off by 23/100ths, or 0.023. And we can't let an error that large be okay. So this is not valid since the probabilities do not sum to 1. Now, it will be okay if we got something like 0.9999998. That's considered close enough to 1. Or something like 1.00001. That's also considered close enough. And you'll get numbers like that because of rounding in the individual probabilities. But 0.977 is too far away, so that's not a valid probability distribution. Let's take a look at the second one here. So we have 6 different values that the random variable x can take on. And first I'm going to scan each individual probability and make sure it's between 0 and 1. What you might notice almost immediately is for the random variable, or for the value 2, we have a negative probability. So I don't even need to bother to see if they sum to 1 because that is a deal breaker right there. So this is not valid because there is a negative probability. Okay, and finally, let's look at the last one. So again, 6 values that the random variable x can take on. And notice that we have some negative values for x. That's okay. The random variable can take on pretty much anything, positive, negative values, but still, since we're talking about discrete, they have to be countable numbers. But it's okay for the random variable to be negative. It's not okay for the probabilities to be negative. So going through here, looking at these probabilities, we don't have any negatives. That part's okay. That's satisfied. Let's double check to see that they sum to 1. When I add those up in my calculator, they sum to exactly 1. So remember, it's okay if you have a distribution where it's a little bit off for 1, but that one's exactly 1. So this is a valid probability distribution. So we want to keep an eye out for that, because if a probability distribution is not valid, then we don't want to bother with finding the mean or all these other calculations that we're going to work on. So we want to check to make sure that a distribution is valid in the first place before we move on with any calculations. Okay, let's take a look at example 2. Complete the table below to create a legitimate probability distribution. Well, now you know what goes into a legitimate probability distribution. I have to have probabilities that are between 0 and 1, and all the probabilities have to sum to 1. So here we're missing 2 values. Well, we already know we're not going to pick anything negative, and we're not going to pick anything that's higher than 1. So we know not to do that. But we need to figure out what these 2 values should be in order to make them sum to 1. So the first thing you can do is sum the values that are there. So 0.27 plus 0.18 plus 0.09, and that gives me 0.54. And if I subtract that from 1, that tells me what the sum of the other 2 should be, which is 0.46. Now all I have to do is make sure I pick 2 values such that they add up to 0.46. So it doesn't matter if they're completely even. If I split it down the middle, 0.23 and 0.23, I could do that. Or I could make one of them 0.16 and 0.30. So there's a lot of different answers that are correct here. You could choose 0.40 and 0.06, however you choose to split them up, as long as they add up to 0.46. And that's pretty much it on that one. Okay, now again, previously we found the mean of a frequency table by multiplying each frequency by its midpoint or class value. And we also did that with weighted means. We'll do something similar here for finding the mean of a probability distribution as well. The mean for a probability distribution is also called the expectation or expected value. And it's simply what is expected to happen over multiple trials or in the long run. So it's exactly the same as the average or the mean, but it's referred to as the expectation or expected value. So here, more formally stated, is the expected value formula. Mu, remember that notation for the population mean. If it were a sample, we would say X bar, but typically for random variables, you're going to see Greek letters. So mu equals E of X. This notation is used for expected value. Even though it's the exact same thing as the mean, you'll see that notation, so make sure you become familiar with that. And the formula tells us the sum of each X value times its probability, its respective probability. So each X value times its probability, then I add them all up, and that's going to be the mean. Be careful though, when you do calculate expected value, you might not get a whole number. So if we're counting something like, what number comes up on a die, I can tell you right now the mean of that is 3.5. Well, it's not possible to get a 3.5. You can get either a 3 or a 4, but the mean is still truly 3.5. So don't round it up automatically. Just know that sometimes when you're calculating the mean, you might get a decimal even if you started off with whole numbers. All right, let's take a look at example 3. The USA Today reported that approximately 25% of all state prison inmates released on parole become repeat offenders while on parole. Suppose the parole board is examining 5 prisoners who are up for parole. Let X equal the number of prisoners, actually let's call this parolees. Parolees out of 5 on parole who become repeat offenders. And we're given this probability distribution. So what this says is the probability that 0 become repeat offenders is 0.23. And the probability that 1 out of the 5 becomes a repeat offender is 0.396, and so on. So that's what this is represented. Part A, find the probability that 2 or more parolees will be repeat offenders. Well, that or more is really important. What that says is I want the probability that either 2 or 3, because that's more, or 4 or 5 become repeat offenders. So either just 2 or 3 of them, or 4 or 5. So to find the total probability that 2 or more parolees will be repeat offenders, we add up all the individual probabilities. So I have 0.264 here, 0.088, 0.015, and 0.001, and that sums to 0.368. Now, by contrast, if we were asked instead find the probability that exactly 2 parolees will be repeat offenders, we'd only have to state the 0.264. But when it says more than, then we're adding up 2 and 3 and 4 and 5. Okay, let's take a look at part B. I'm going to move this over here for a little bit more room. Find the probability that less than 2 parolees will be repeat offenders. So if it's less than 2, now take into consideration it didn't say 2 or less, meaning including the 2. It's strictly less than 2. So that means either 1 parolee is a repeat offender or none of them. And I'm just going to sum up those 2 probabilities, which gives me 0.633. Now, I don't know if you noticed, but we have 0.368 for 2 or more and 0.633 for less than 2. And if you sum those up, that sums to 1. Technically, I get 1.001, but we'll say that that's 1. So those 2 are actually complements of each other. 2 or more, and then less than 2 covers our whole entire sample space. So you might use that concept sometimes when you need to make a calculation. And finally, part C. Find the expected number of repeat offenders out of 5. So this is the average, meaning out of the 5 parolees, in the long run, how many of them will be repeat offenders? So here's what we do. We take each random variable, each value that random variable x can take on, and multiply it by its probability. So this is the mean. Mu is equal to 0 times 0.237 plus 1 times 0.396 plus 2 times 0.264, and so on for each value in the probability distribution. And let's see what we get with that. So after punching into my calculator, I get 1.253. Okay, and be careful, the mean is not a probability. It's okay for it to be more than 1. In fact, this is telling us how many of the parolees will be repeat offenders. As we mentioned before, I'm not getting a whole number. I'm not getting 1 or 2. I'm getting 1.25. And that's just because it's a calculated statistic. But if we were to explain this in real terms, we would say about out of 5 parolees, about one of them would end up being a repeat offender, which makes sense with the 25%, because that's 1 out of 5 is 20%. It's a little lower, but it's kind of in that ballpark of the original probability that we were getting. So it's okay if the mean is a decimal, perfectly okay, but what it really says is about 1. Sometimes there might be 2, but when you average it over the long run, we say 1.2. Next, we have the variance. The variance for a probability distribution is found in a similar way as we did before. And remember that the relationship between the variance and the standard deviation. The variance is just the square of the standard deviation. So the way we found it before here with our notation sigma squared, we took each value, subtracted off the mean, whatever that difference was, we squared it, and then we multiply it by the frequency. And in this case, we're multiplying by the probability. So we do that for every value. Take each value, subtract off the mean, square it, multiply it by its probability, and then we add all of those up. That's the variance. An alternate formula is to take each value, square it, multiply it by its probability, add all of those up, and then subtract off the square of the mean. This formula is considered a computational formula. It's a little easier to compute because you're not having to keep track of so many subtracted square, subtracted square, subtracted square. So you will use this one from time to time. And then you also see an alternate notation. So this third formula is really the exact same thing as the second, but it's written in a different way. So you'll see VAR for variance of x is equal to E of x squared, which is this right here, where you take the x's squared and multiply it by its respective probability, minus E of x quantity squared. So here, this is just the mean after we found it, and then you square it. Let's go ahead and try out finding the expectation and variance of this probability distribution. So example 4, and I picked something very small so we wouldn't have too many calculations here. So find the expectation and the variance. Well, remember the expectation is exactly the same thing as the mean. So to do that, I'm going to take each value and multiply it by its probability. So we only have 3 here, and that shouldn't take us too long. So this ends up being 0.9. So that's the mean. Now, if we did the variance kind of the old way, what we're used to, I take my value, subtract off the mean, square it, and multiply by its probability. So take the next value, subtract off the mean, square it, and multiply by its probability. And then the last value, subtract the mean, square that, and multiply by its probability. We're kind of going step by step here. If I square the difference, that's 0.81 there. .01 here, and it should be 1.21. Yeah, 1.21 here times 0.15, and then I can just multiply and add. And after plugging all that in to my calculator, I get 0.39. So that's doing it with the first formula presented here. Let's get rid of this. Where we take each value, subtract the mean square, and multiply by the probability. Here's an alternate method, and I'll leave the decision up to the student as what's easier or makes more sense for calculating the mean. So the alternate method, I'm going to use that other notation, the variable of x equals the expectation of x squared minus the expectation itself squared, which is truly just the mean. Well, remember the expected value formula said to take an x, multiply it by its probability, and then add all those up. If I have e of x squared, then I'm going to take x squared, multiply by its probability, and add those all up. The way that this formula works, whatever's in the parentheses is what gets multiplied by p of x. So if I had e of x to the 7th, I take each x raised to the 7th power, multiply it by its probability. If I had e of x to the 100th power, it'd be e to the 100th power times the probability. So that's how that formula works. So for e of x squared, I would take 0 squared times 0.25, and then 1 squared times 0.6, and 2 squared times 0.15. So we have 0.6 plus 0.6, which is 1.2. Now for the variance, I plug in the pieces that I have. So e of x squared I found here is 1.2. E of x we just found up above in the previous step. Remember, that's the mean. So this is 0.39, but it's going to get, oh, no, 0.9 rather. And it will get squared. So 1.2 minus 0.81, which comes out to 0.39, just as we got above. So for me, it's easier to square integers, the 0, 1, 2, and multiply by the probability and work it out from there, than taking all these differences, having to square those, and then multiply by the probabilities. But it's up to you. You just might find that the alternate method is a little easier to calculate.